Awesome. Going to give it a couple minutes for folks to join, and then we'll get started. All right, thanks everyone so much for joining us today for this webinar on winding down end of service and recycling for wind energy. I'm going to start with some webinar logistics. This webinar will be recorded and posted to the NREL YouTube channel and the US Department of Energy's DOE's Wind Exchange website. We will also send out a recording to all registrants a couple weeks after the webinar, so you will get the slides and a link to that recording in your email. You can post questions using the Q&A function during and at the end of the presentation, so feel free to pop your questions in there. We will answer some of those in writing, and then some of those also at the end of the webinar, we'll pose them to the speakers. We also send out a Q&A document after the webinar to all registrants along with that recording, so any questions that we don't get to, we will give a more detailed response in writing. In this webinar, we will cover an introduction to wind energy end of service activities. This will go through everything from repowering and land restoration to decommissioning and component processing, as well as some of the policy and planning aspects of end of service as well. Then we'll have a presentation on recycling of wind energy components that will go through different processes that are being expanded and researched to figure out how we can recycle some of the more tricky components like blades and other composite materials, and then talk about scaling up the recycling industry as well. Then we'll have just a short overview of some of NREL and DOE's efforts related to end of service and recycling, and then we will have a 15-minute Q&A at the end. I will now introduce our speakers. So Chloe Constant is a senior project leader at NREL, where she oversees the wind energy stakeholder engagement and outreach and workforce development programs. She worked on NREL's recent wind energy end of service community and stakeholder engagement project, which engaged industry, community, and government stakeholders to better understand diverse perspectives and considerations for wind energy end of service activities. Prior to joining NREL at the end of 2019, she spent 10 years at E.ON, now RWE, where she worked in various positions for the renewables business in Europe, most recently as a director in mergers and acquisitions with a focus on land-based and offshore wind. Derek Berry is a senior engineer at NREL and the director of the wind turbine technology area within the Institute for Advanced Composites Manufacturing Innovation, a Manufacturing USA institute. He leads an NREL and IACMI team in the research of innovative composite materials and manufacturing for wind turbine blades and other components. Previously, he was the NREL engineering supervisor at the Wind Technology Testing Center in Boston, Massachusetts, where he was responsible for large-scale wind turbine blade testing engineering operations. He also serves as the operating agent for the International Energy Agency's Wind TCP Task 45, recycling wind turbine blades. Prior to joining NREL, Derek spent 15 years as a wind blade design, manufacturing, and testing engineer at TPI Composites, and he is a graduate of the U.S. Air Force degree in aeronautical engineering. And now I will pass it off to Chloe.
Great, thank you, Matilda. So before we really get into the topic, we did want to just pause briefly and talk a little bit about why it's important. So for starters, wind turbines have a typical lifetime of 25 to 30 years, after which time they're going to be repowered or decommissioned. And I do want to just note that doesn't mean every individual turbine component is actually designed to last for that long. So while foundations and towers and things like that are expected to last that long, other components are going to need to be repaired or replaced earlier. But we do have legacy projects that were installed in the 80s, 90s, and even early 2000s that have already been decommissioned or repowered. And there's many, many more that are beginning to get to the age and stage where these activities are going to be carried out. And maybe to throw some figures out to give some scale of the topic. So as of 2023, there were more than 73,000 wind turbines deployed across the country. Obviously, this number is a bit higher now, and there's many more projects in the pipeline, so it's just increasing. And there's going to be a number of decisions that need to be made related to end of service that actually happen throughout the project lifetime. So including already in project development stages. So it's not enough to wait till a project is getting to the end of its lifetime. These decisions need to be thought about, talked about, and taken earlier in the process. And maybe one other note before we really get into things, we're focusing mainly on land-based wind in this webinar. Some of this is going to be relevant for offshore wind as well, but there's a lot of other additional considerations and differences that are important. And yeah, we only have an hour, so we're going to focus mainly on land-based. But with that, I do want to provide some grounding for some of the various activities and aspects that we're talking about when we say end of service. And I'm going to start with repowering because this is quite a broad term. It can cause some confusion and in some cases even seem like a little bit of a misnomer depending on the situation. Broadly, it's referring to the retrofitting or replacement of wind project components, and that can be either in part or in full, and we'll get into that difference in some of the next slides. And I do want to highlight that this is different than simply repairing or replacing a damaged or a worn out component that happens, on an as needed basis and is typically sort of one component at a time as like a project, or excuse me, as a problem arises or like is expected to arise. But instead, repowering is planned typically and carried out across all of the turbines, or at least many of the turbines, and may include multiple components. So like blades, maybe the entire nacelle, rather than a single component that might be experiencing issues. So like a gearbox or something like that. There are a number of reasons why repowering might be done, including extending the life of a project or enabling increased power generation. And we'll talk about that more a little bit later as well. But repowered projects typically do use existing infrastructure and grid connections, and that gains some advantages. So now I want to move on to partial repowering. And this is where only certain turbine components are replaced. So what this means is that typically the project footprint, so where the turbines are, isn't typically impacted, and the turbines themselves might see some changes, but they're going to be limited. So we wanted to give an example of that on the slide here. You can see we're showing a sort of indicative or an example of a partial repowering where there is a height difference. So in this example, the capacity of this turbine is being increased from 2.15 megawatts up to 2.45. And that seems sort of modest, but if you're doing it across a whole farm, it really can have a big impact. So in this example, the tower is staying the same height, and so the hub height stays the same, but the blades are getting replaced in this example, and so that blade length is increased, and that's going to mean an increased rotor diameter and therefore a higher tip height. So in this example, it's a little over 11 meters or just shy of 40 feet for those of us that don't speak metric. But again, this is just an example to provide some perspective. And there are a number of different approaches to partial repowers that are going to determine what it ultimately looks like. So for instance, the components that are typically replaced may or may not include things like blades, like I mentioned, but also gearboxes, hubs, main shafts, main bearing assemblies, that sort of thing. So it can vary project by project. But partial repowers do use the existing towers and foundations, and that's one of the ways it sets it apart from, say, a full repowering. And I did also just want to give an indication that partial repowering typically occurs a little bit earlier in the project's lifetime. So usually in the first half, and I think we did do some assessments that put the median age of a partial repower in the US at about 10 years into its lifetime. But maybe moving on to full repowering. So with full repowering, what we're talking about is the existing turbines being removed and replaced completely with new ones. And this is where I think the term repowering can be a little bit confusing. But the idea is you're replacing the older, potentially smaller, less efficient turbines with newer models that are going to be typically larger, more efficient, and therefore mean that fewer are needed to generate the same amount of power. And as opposed to partial repowers, full repowers are more often considered towards the end of a project's lifetime, maybe as an alternative to the full decommissioning of a project. So again, we wanted to provide a little visual as an example of what a potential repower could look like. So in this case, what we're showing is that there are fewer turbines, but larger turbines, as opposed to the original project. But let's talk a little bit about repowering trends and what's happening in the US market. So if we move to the next slide, there's some ebbs and flows in terms of the rate at which these projects are getting repowered, and you can see that in the graph that we have here. But we're generally seeing it become increasingly common. And to put some numbers on that, so far in the US, more than 14 gigawatts of projects have already been fully or partially repowered. And analysts estimate that there's a potential for an additional 16 gigawatts of full or partial repowers through to 2026. And looking at 2024, it's estimated that repowering could add 6.5 to 7.5 gigawatts of power to the grid. So that's nearly half of all new capacity. So it really is a lot of additional power that we're talking about when we're talking about repowering. And I should note that those numbers do include both full as well as partial repowers. So there are a number of reasons why we're generally seeing more repowers. Again, the potential to extend the project's lifetime, maybe a project that has really great wind resource. It's also potentially taking advantage of technological advances, which there are a lot of, and have been and continue to be. There's also things like requalifying for tax credits, and that's a very popular one at the moment that's driving a lot of these decisions. And there's obviously some cost savings from reusing existing infrastructure that might make it more attractive than a brand new project. One other thing I did want to know about repowers, though, is that they are going to be subject typically or oftentimes to a permit review and renewal. And this is particularly true of full repowers, where it is a sort of redesign of the project. And this reflects the fact that repowers do change the characteristics of a project. So it may also change the impacts of projects. And this can be both in positive and negative ways. So for example, if we have higher capacity, it might mean higher landowner payments. But if there are fewer turbines, because they're bigger and more efficient, it might mean fewer landowners involved. So landowners that were previously getting payments that no longer are. It also might result in increases to tax revenue and the potential for increased or even new community payments, but it might also mean taller, more visible turbines. So there's a lot of factors to consider when we're thinking about repowers. But with that, I want to move on to decommissioning. So this is the removal of a wind energy project at the end of its operational life or when it's being repowered. So as I mentioned before, in a full repower, the turbines are being completely replaced. And so there is a certain amount of decommissioning that happens as part of that process. But decommissioning activities include removing of the turbines, and there are various ways to do that. So for instance, it can be done through felling when there's a sort of controlled demolition of the turbine, or using cranes to disassemble it section by section, like what's in the photo here. It also includes the removal of the infrastructure that's going to be below ground, so things like foundation and below ground cables. This can vary project to project. So for instance, sometimes foundations are only partially removed down to about 3 or 5 feet is quite common. And things below that depth may be left in situ or left in place. And that's something that would be agreed with the landowner and in line with regulations. And some reasons for leaving things in situ is just lessening the disturbance than would be experienced if it got pulled out. But decommissioning activities also include removing the associated infrastructure that's above ground. So any above ground cables, access roads, fencing, maybe even substation. But again, this can vary. So for instance, we've seen projects where it's been agreed to leave certain infrastructure in place for continued use. For instance, maybe a farmer wants to leave one of the turbine access roads for their future use. But again, in line with their needs and regulations and reflected in the agreements. And then finally, it's restoring the land to agreed upon conditions. But I would like to note, decommissioning an entire project currently is pretty uncommon in the US. And that's generally speaking, because there remains quite good opportunity to use some of these sites. So we're seeing more often that sites are getting repowered than fully decommissioned. So that's something to keep in mind. So moving on to decommissioning regulations, I've been sort of mentioning regulations and things like agreements with landowners and decision making, but regulations do come into play a lot regarding what can or cannot be done. These can be sort of at the hyper local, county, state level. So various levels that these requirements or standards or regulations can set in. For instance, there's often a requirement for project owners to submit a decommissioning plan that's going to describe how they intend to remove the infrastructure and process the waste and restore the land and things like that gets agreed up front. We did also want to just call out another common thing that's currently being regulated quite a lot, and that's a form of financial assurance. So that's something like a decommissioning bond, maybe a parent company guarantee or letter of credit. And this is to ensure that there is going to actually be money available to carry out the agreed decommissioning activities when they do happen. This is quite important. And it's often a concern for communities, and particularly ones that may have experienced abandoned infrastructure in the past, either from other industries or even some of the legacy cases from the early wind industry. So it's important to get right. But when you're talking 25, 30 years out, there's a lot of uncertainties in terms of what things will cost, so accounting for like inflation, but also different standards and practices. And that might make it cheaper and easier to do certain things, like maybe recycling as the technology progresses, but it might also account for sort of increased costs. So it's important to reflect that while also taking into consideration that these financial assurances do come at a cost. So important to get the land balance or get the balance right. Yeah. Moving on to land restoration, and just very quickly on this, it's the process of restoring the land to the agreed upon conditions. I'm going to sound a bit like a broken record because this is going to vary and be in line with what's agreed with the landowner. It does not necessarily mean the state it was previously. So it's going to be in line with what landowners might plan to do with their land and also with the relevant ordinances or regulations. But those sort of activities include things like reseeding vegetation, maybe repairing damaged drainage tiles, decompacting the land, restoring the grade of the land, that sort of thing. But moving on, so we've taken our turbines out of service. Well, now what do we do with them? So in dealing with the components that we take out of service, there are broadly three main options: landfilling, reuse or repurposing, or recycling. And there's a lot of factors that go into what's decided and what approach is taken. So things like cost, regulations, obviously, maybe capacity for certain activities, location and transport can all impact this decision. So for example, if nearby landfills either aren't willing or able to take waste, that's going to make landfilling more expensive. And likewise, there are ways to make recycling and reuse and repurposing more attractive. But let's start with landfilling. And I should say that quite a lot of an actual turbine is quite easily recyclable, and Derek is going to get it more into that. But there are components, and particularly the composite components like blades, that are going to be more challenging to recycle. So currently, landfilling is typically the cheapest and most common option for those components like blades. And blades do get a lot of public attention. We wanted to share some numbers to put it into context. So in 2018, so this is a little ways back, so assume this number is going to be a little bit higher. There were about 50,000 tons of blade waste that was being managed by landfills. At the time, though, that's in comparison to 291 million tons of municipal solid and construction and demolition waste in the US. But still, it is waste, and it can present other challenges. So like the figure I just gave related to weight, but blades are designed to be light. So they're actually taking up disproportionately large amount of space relative to their weight. They are large, they are awkward. They may require specialized equipment, capacity, trained personnel to be able to process them, things like segmenting them and even just accepting them into landfills. So that can be challenging. And there are some economic benefits related to being able to accept blade waste in landfills. But we are seeing that some communities are starting to enact landfill bans, and there are even sort of countries across the globe that are completely banning the landfilling of blades. So we do want to make sure that we're looking at other options like the reuse, repurposing, or recycling of them. So moving on to reuse and repurposing. When we say reuse, we mean things like using parts as replacement parts. This isn't so common, so I'm not going to spend a lot of time on it. But looking at repurposing, this one sometimes gets a lot of attention, like this photo of a bridge in Poland that's made from blades. So it can be quite cool and useful to reuse blades in some of these creative ways. Um, but the caveat there is, even though you can be doing this, when you think about the scale of blades coming out of service, it might not be scalable or cost effective to repurpose all of them. So as a reminder, we're talking as of 2023, 220,000 blades that are currently in service that at some point will be coming out of service. And that's all to lead into the topic that we're going to spend the rest of the webinar focused on, and that's recycling. So with that, I'm going to hand it over to my colleague Derek to take it from here.
Thanks, Chloe. Appreciate it. And hello, everybody. What I'd like to do is then focus now, as Chloe had mentioned, on recycling, and I'll talk a little bit about recycling on sort of the turbine level, and then focus more on the components that are more difficult to recycle, as Chloe mentioned, the composite materials, the blades, and other composite structures within the turbine. So about somewhere around 90% of a wind turbine is easily recyclable at the end of life. A lot of metal components and above ground components, and they have been recycled for a long time now, actually. But it's really the blades, the nacelle cover, the rotor, the nose cone on the rotor that are composite materials that are much more challenging to recycle. And so those are the components that we have spent some time over the past about decade looking at how can we recycle. As Chloe mentioned, we can extend life, we can reuse, we can repurpose, but really we're looking for effective end-of-life recycling options for these composite materials. I jumped in the wind industry in 1995, so I've been doing this for about 30 years. And for the vast majority of my time in the wind industry, nobody was thinking about recycling of blades at the end of their life. And then really even 10 years ago when we started IACME as a composite institute, we started to sit down with all the OEMs and asking the blade manufacturers, where on their list is this recycling of blades at the end of life? And it really didn't even make the list back then. But there has been a sea change of awareness and of importance placed on developing methods to recycle blades at end of life. So really, it's been a great progression there. Also, I just want to mention a couple other components. Foundations are not easy to recycle at the end of life. These underground foundations, often they're left in place, but they can be ground up and used as aggregate in other processes as well. And then the rare earth elements in the generator, and specifically for permanent magnets, are sometimes difficult to recycle rare earth elements. However, because of supply chain difficulties with mining and receiving these rare earth elements for future wind turbines, it is essential for us to be able to put in place ways to effectively recycle rare earth elements and reuse them into generators or other components outside of wind down the road. Next slides. Yeah, so this is it's a great graphic showing you the wind turbine itself and kind of what is recyclable. And really kind of the important thing here is that we've highlighted the fact that every single component, every single material in a wind turbine is recyclable. However, it's not always as easy as other components. As I mentioned, you'll see here in the nacelle cover, the blades and the rotor cover or the nose cone are the ones that are made out of composites, and therefore landfill is an option there, but recycling is as well. And it's our job, national labs, partnering with universities and industry to develop pathways to recycling of these composite components. You'll see, though, that a lot of the other components here, the towers and the internal parts of towers, the foundation itself, and the inside parts of most of the nacelle are already and somewhat relatively easily recycled right now. Okay, next slide, please. So we're trying to understand the volume of waste materials coming from wind turbines that are being decommissioned and trying to plan for that. And we kind of see this wave coming right now. You'll see in the upper graph on the right-hand side, and both of these graphs are under high wind energy deployment scenario. And so looking at sort of what we think is the top end of what we might see between now and 2050 for the deployment of wind energy. But this is actually, a lot of this is based on what is already out there. You know, Chloe talked about the fact that we have so many wind turbines and wind turbine blades out in the United States, and so this is kind of based on the projection of those coming to the end of life, as well as some of the turbines will come into operation in the coming years. But you'll see up on the top is the annual during the decades, the decade we're in now, the second column, and the third and fourth column, the decades of the 30s and 40s, what that annual total waste looks like, and then the cumulative down bottom. And so we're going to be approaching about 140 million metric tons of waste by 2050 of total waste from the turbines being decommissioned. You'll see that the road aggregate and concrete, the yellow and the dark blue sections, as well as the composites right above that, the light blue sections, are the areas that are probably going to grow fastest over that time, and the ones that we had to put considerable amount of effort into trying to make sure that we have sustainable ways to recycle these components. So next slide, please. So here you'll get a sense of, and Chloe mentioned some of this, we have right now per year about anywhere between 3,000 and 9,000 blades that are being taken out of service, and that we're looking to reuse, repurpose, recycle one of those options before we put them into a landfill. And you'll see this kind of up and down. That chart on the left-hand side shows you that's not consistent year to year, and that's for a lot of reasons. I mean, even when we established wind and started building and putting wind turbines in the ground, it was actually a sort of an up and down every year. But bottom line, if you look at the right-hand graph, we are going to be approaching 250,000 blades, end-of-life blades by 2050 that we have to have some sort of solution for beyond landfilling. All right, great. Thanks, Matilda. Next slide, please. So I'm going to start with mechanical recycling. So at the end of life, once decommissioning happens, once those blades are taken off the tower, whether you fell a turbine with dynamite or you take them down with cranes, and then you have to figure out what to do with those blades. They're on the ground next to the turbine. Oftentimes, you'll do some decommissioning processing right there at the site. At the very least, you'll cut blades into sections. You won't ship a blade on a truck like you did on the way out to the site because it's just far too expensive. So you cut them into sections, or you might actually do a bunch of downsizing, sort of mechanically shredding that blade at the site, because really shipping a shredded blade, the volume, the weight stays the same, but that volume will actually get much smaller when you, a lot less air that's inside of a blade when you shred that down. And it's more cost effective to get that to a recycling site. But this mechanical recycling that we're talking about can take that shredded blade. It can be used in cement co-processing to put it into a clinker and help with the use in material for cement, or as a fuel source to make cement. But this mechanical fiberglass and carbon fiber, and it also has balsa wood core and foam core in there. Other components that are inside that wind blade can reuse if it's chopped down or mechanically recycled fine enough as sort of aggregate and other materials as well. Reprocessing that with concrete, but it can also be with other composite processes as well. So that's mechanical recycling, and we'll come back to this in a little bit, looking at the efficacy of this. Next slide, please. So we also have pyrolysis, or what's called thermal decomposition or thermal recycling of blades. And basically, it's using heat to recover the glass fibers and the carbon fibers as well that are inside that blade. And it can also recover core material, as I mentioned, balsa or foam core, things like that. But basically, using heat or pyrolysis to kind of melt away the resin of the blade, the matrix of the blade, and then recover the solid elements of fiberglass carbon fiber. Now, one of the things here, there can be some damage to the fibers, the carbon fiber and fiberglass. Also, depending on how well you perform the pyrolysis, it could be that some of the fibers that are long fibers in the blades, we have fibers, long straight fibers that run from the root of the blade all the way to the tip for the strength and stiffness of the blade and the spot gap. Those can sometimes be chopped up in this process as well, and therefore the material properties don't always come out as 100% of what the strength and stiffness of those properties were in the blade itself. So there are some processing setbacks here as you go through this. The next one is looking at solvolysis. And on the next slide, chemical decomposition or chemical recycling of blades. And this is where you look at solvents, mixing water and or alcohol together or other solvents, also with heat and pressure oftentimes, and then degrade the plastic components or the resin system, the matrix of the blade, and then recover the carbon fiber and the fiberglass, and then reuse that into new composite processes. So right now, we're looking at mechanical, we're looking at thermal, and we're looking at chemical as three possible ways to recycle blades at the end of life and recover material in some different forms at the end of its life to use into new composite products out there, whether it's in the wind blade industry or maybe in vehicles or infrastructure or marine, other types of cross-cutting industries, other applications with composites as well. Next slide, please. Yeah, so looking at the mass yield analysis. So on the chart on the right-hand side, we're looking at all the different end-of-life scenarios. The first one being landfill, and then looking at cement co-processing, and then some recycling, mechanical pyrolysis, microwave pyrolysis with a little more effective pyrolysis, and solvolysis, and understand where does that material go? How do we utilize that material at the end of life? Now, not surprisingly, in the landfill, on the far left of the entire gray is lost or goes to a landfill. That material is not toxic. It doesn't present a problem for being buried in the ground, but it's not reused again. It's not sustainable or sort of a circular economy for materials to be used again and again in blades or other structures. So that's something we want to avoid. But you can see that all the other recycling or end-of-use processes have some sort of combination of some material that is lost, very little in the other processes, the gray up on top of those bars, but then looking at some that's incinerated or produces oil and other gas products, but really looking at the primary and secondary recycled material. And really what that means, the primary material is material that has very similar mechanical properties to the original composite material, and we can use that in very sort of high load applications for composites for its second and third life. Whereas the secondary solid recycled material means that during the process of recycling, it had some downgrading to the mechanical properties. And so it is sort of a little bit of a downcycling rather than recycling, where you're using that in composite materials that might not have as much stiffness or strength, as much material property requirements as blades do at the beginning of their life. So you can see there, microwave pyrolysis and mechanical recycling actually use more of the material than the other processes, the more of the mass that comes out of the blade than the other processes here. However, and I'll go to the next slide here, we also look at LCA. So life cycle analysis of all these operations. There's a possibility to come up with many different ways to recycle blades, but a couple of different things have to come into context here. One is cost. We have to find cost-effective ways to recycle blades at the end of their life. But the other is looking at a life cycle analysis and LCA and understanding how energy intensive is the process to recycle those blades? How much energy do we use to recycle those blades? What is the greenhouse gas emissions, the carbon footprint of the process to recycle those blades? So here at NREL, along with Oak Ridge National Laboratory and Sandia National Laboratory, in conjunction with Department of Energy, Wind Energy Technologies Office, WEDO, we have done some studies recently looking at LCA, and this LCA brackets around the recycling process. In other words, it doesn't go back all the way to the boundary of the LCA, doesn't go all the way back to the manufacturing of the wind turbine blade, but the actual recycling process, and then evaluating landfilling, cement co-processing, and then pyrolysis and solvolysis for the efficacy and the metrics in this case of the greenhouse gas emissions. And so you'll see for landfilling, there's not a whole lot of greenhouse gas emission, but you also don't get any credit for recycling those. The green bars down bottom are the credit in the other processes that you get for displacing virgin material that might be used in future composite materials, and therefore you get a credit from greenhouse gas emissions on those. But ultimately, adding everything together, the transportation, the reduction of materials, decommissioning before transportation, and then the recycling process, you'll see the little black diamonds there are the overall efficacy for the carbon footprint of the recycling process. So you see that landfilling is a little bit above net zero for how much greenhouse gas emission occurs during that process. But if you look at cement co-processing, mechanical recycling, and microwave pyrolysis, those are the ones that resulted in net negative greenhouse gas emissions when you take into account the credit that you get for displacing the use of other materials in the future. I do want to mention that this doesn't include blade manufacturing, and this is actually a much smaller amount of greenhouse gas emission that is put out there that compared to blade manufacturing. We are also, topic for another webinar, we're looking at reducing the amount of waste in blade manufacturing, being able to recycle and reuse that waste in blade manufacturing, and also looking towards bio-based materials that come in the door to the blade manufacturing plant that have a much smaller carbon footprint as well. Next slide, please, Matilda. Great. So this, we talked about, all the challenges and the opportunities for recycling blades and other turbine components as well at the end of their life. One of the things we're thinking about is how can we redesign blades now so that in the future, blades and composite materials are easier to recycle than they are now. When we designed blades 30 years ago, 20 years ago, we are designing blades to be indestructible at the end of their life, very lightweight, very tough, and very difficult to break down. That's what we want in the field as a blade is up on the turbine. But now we're looking at ways, but that makes it very difficult to break down at the end of their life for recycling. We're looking at ways to design recyclable by design blades in the future. So here at NREL and our projects with other industry partners and other national labs and universities have looked at, can we use thermoplastic materials? We have typically used polyester, vinyl ester, and epoxy materials, thermoset materials that are very difficult to break down at the end of life. And we're looking at Arkema Ilium in situ polymerized thermoplastic resin system that at the end of their life with heat and pressure can be reversed, get the resin back, and also get the fiber, the carbon fiber, glass fiber, other components back as well, and reuse all of that for either future blade components or other applications for composites as well. And then we've also, the industry has been developing reversible thermoset resins. So in the chemistry of the epoxies, putting some cleavage points in the chemistry that at the end of the life of a thermoset blade that are maybe being produced now with these reversible thermoset resins, you can also reverse that process and recover the resin, the thermoset resin, and also the fiber and other core materials of the blade itself. So those are some of the things we're looking at now. Next slide, please. So that brings us to where we are in the state of blade recycling in the United States today. It is still a fledgling industry. There's no standard process. We're still working through the technology, the cost effectiveness, the community engagement with different processes that might exist in their neighborhoods, in their states. And we're not at a point yet where there's a standard process that these blades or any composite materials for that matter have a path to recycling. As we mentioned, there are 3,000 and 9,000 blades coming out of service each year right now. And we do have some capacity between Carbon Rivers and River's Edge and some other companies to actually recycle about 3,000 or a little bit more blades per year. So we have that capacity. However, that supply chain is not really smoothly in place. Regionally, it might differ region to region where you are in the country and where the blades are coming down from the towers, whether they're in Texas or Iowa or Wyoming, it may not be close to where those recycling facilities are. And so developing that supply chain for recycling composite materials, blades in this case, is really important. And I think, and Chloe mentioned this a little bit as well, the amount of waste from blades is tiny compared to overall waste, non-composite waste, but even composite waste as well. So we are now partnering with other industries, the marine industry, the automotive industry, the aerospace industry that uses quite a bit of composites and saying, hey, can we reach a critical mass of composite material at the end of life of both blades, but also all of these other structures to get us to a point where we can develop these supply chains around the country to really kind of enable the recycling of composite materials and also bring down the cost. And with all of these different applications and components being part of the research and the drive to recycle composites at the end of life, that'll also enable kind of the reduction of cost by scale by the end of their life as we move on. Next slide, please. So finally, there is a challenge here. Right now, recycling is expensive. It's more expensive than putting blades into landfills. I lead, along with Justine Boson out of DTU in Denmark, I lead an IEA task for wind blade recycling. And a lot of our members are part of the European community. And they are now, as Chloe mentioned, starting to ban blades going into landfills. That may not happen anytime soon in the United States. We have a whole lot more room in our landfills, and our policy isn't the same as what the policy in Europe is. However, all of the blade manufacturers, or turbine OEMs and blade manufacturers, are looking towards blades at their end of the life around the world and trying to make sure that there is a cost-effective and a solution for recycling these blades at the end of their life. I mentioned earlier that supply chain is so important. Right now, we don't have a whole lot of key recycling facilities nearby where the turbines are coming down, and we're trying to correct that and build this recycling supply chain at scale. And then finally, there's this inconsistent flow of blade waste. We see up and down every year, but if we are partnering with other industries, that will then be that sort of will smooth out with the amount of composite waste every year from different applications, different industries. That'll help us make the case for a cost-effective and low energy intensive and low greenhouse gas emission solutions for recycling blades, nacelles, covers, rotocones, and other composite materials at the end of life, to really get to a point where blades can be on par with the rest of the turbine, the rest of the other metallic components of the turbine that are already recycled at a high rate in the United States. So I think that's it. Matilda, I think the next slide is maybe moving on. Yep, great. Thanks for your time. I look forward to answering questions at the end of the presentation here. Thank you.
Awesome. Thanks so much, Derek. I'm going to wrap up before the Q&A with a few slides about NREL and DOE's efforts to support recycling and just general efforts related to wind end of service. The first one to highlight is Carbon Rivers, and I think Derek just mentioned Carbon Rivers. This is a company that, and through a partnership with the University of Tennessee, Knoxville, received funding from the Department of Energy's Wind Energy Technologies Office to scale up their process to recover clean, mechanically intact glass fiber from blades. Carbon Rivers uses a pyrolysis process to separate organic components of the blade, like resins and polymers, from inorganic fiberglass material. The organic products are then converted back into hydrocarbon, which can be used for energy production. And because of this, the process has a net positive energy output, meaning that it ultimately creates more energy than is used to carry out the process. The recycled glass fiber can also be used in place of virgin fiberglass in different composites, new composites, or even incorporated into that virgin fiberglass, creating circularity for the material. Carbon Rivers has commercialized this process and operates a recycling facility in Tennessee where they accept blades and other composite materials from different industries like the auto industry and marine industry. And they also have expansion plans underway to open additional facilities in other states like Texas. Next, I wanted to highlight the work that NREL has been doing on end of service and recycling across 3 projects that are funded by the Bipartisan Infrastructure Law, or BILL, over the last several years. The first is the Wind Energy End of Service Community and Stakeholder Engagement Project, which engages industry, community, and government stakeholders to better understand diverse perspectives on wind energy end of service. This involved community listening sessions, roundtables with industry and governments, and interviews over 2 years with people across the country to better understand both technical aspects of end of service, but also things like community impacts, policy and planning, economic impacts, and things like that. The second is the Wind Technology Recycling Assessment, and that is where much of the findings and graphs that were presented by Derek came from. This project is researching and assessing innovative approaches to increasing the reuse and recycling of wind turbine components. This involves a variety of analysis, all under one umbrella of a project, including recycling capacity analysis, life cycle analysis, impacts to levelized cost of energy, and other things like that. And it's a collaboration between NREL, Sandia National Laboratories, and Oak Ridge National Laboratory. And then lastly, the distributed wind recycling roadmap. I noticed one of the questions or comments mentioned distributed wind, so you'll be happy to hear that Oak Ridge National Lab and NREL are working on a roadmap to proactively enable recyclability for distributed wind energy before the expected growth of the industry. So distributed wind energy, which for those who aren't aware, encompasses both smaller wind turbines and the kind of utility scale size of wind turbines, but deployed in smaller numbers. And this is a smaller industry, but is expecting rapid growth. So planning out how there can be pathways to recyclability ahead of time for that industry to avoid some of the challenges that have been faced by utility scale wind in this area. And 2 publications to highlight. The first is the Wind Energy End of Service Guide. This was published in 2023 on DOE's Wind Exchange website by the NREL team. It's an informational resource for communities to better understand repowering decommissioning processes for wind turbines and related infrastructure. It features a lot of the information that was in this presentation and also has some interactive graphics. So for example, the graphic Derek presented that shows the wind turbine components in there, you can look at that in greater detail and click around and see the recyclability of different materials. And then next, the roadmap for recycling wind energy systems in the United States is a forthcoming DOE report. Many of the graphs and findings Derek presented are published in this that is expected later this year. So keep an eye out for that. There will also be a report published from the stakeholder engagement and community engagement project I mentioned later this year, as well as the roadmap for distributed wind. So keep an eye out for those DOE publications. And then lastly, the DOE Wind Turbine Materials Recycling Prize. So in 2023, DOE launched this as part of its American Made Challenges series of competitions. And this is a $5.1 million competition, also funded by the Bipartisan Infrastructure Law, that's intended to help the US develop cost-effective, sustainable recycling solutions for 2 key materials that are in turbines, particularly fiber-reinforced composites and fiber-reinforced composites and rare earth elements. This is a multi-phase competition. The first phase has already been awarded. So in the chat, you should see a link to an article that describes and briefly describes the 20 winners that were selected across 15 states, and the map you can see below describes the projects and processes that they will be using the funding for. The second phase is accepting submissions until July, and this is fewer winners, more money as a way to kind of continue scaling up those processes. And with that, we will move on to the Q&A. Looks like we are getting some great questions in the chat. I think I'll stop sharing and have let's see, Chloe and Derek come back on screen. Perfect. Let's see. We've been having folks upvote so that we can kind of select the questions that were most of interest to folks. So I'll start with the first one that has the most votes. And Chloe mentioned this briefly, but we can get into greater detail. Does repowering require additional environmental review? If the blades are replaced with longer blades, does that change anticipated environmental impacts and mitigation measures?
Yeah, so that's a great question, but one without a simple, straightforward answer. So I think I would start with saying typically, yes. Having said that, it's going to be subject to whatever zoning and regulations are there and relevant for a particular farm in a particular place. But generally speaking, yes, because it's changing the characteristics of the turbine and the farm significantly, it would need to go through an additional review to understand what those impacts would be and the changed impacts.
Let's see, the next question, and I can maybe take a stab at this one as well, that's received some upvotes, is there insight on the flexibility being built into initial development agreements with communities that could help developers reevaluate the decision they make at simple end of life, so that there's some expectation that the economics might look different at the point of decision versus when initial development and permitting was done? And then how can communities prepare for the unknowns in that dialogue? And are there any examples of communities that have done anything proactively like that? I think this is a great question because we try to think of end of service as something that is not just decided at the beginning or the end of the project, but rather there are points of decision throughout. So Chloe mentioned that repowering can happen, as soon as 10 years into the project's life. So decisions being made at that point may look very different than if the decision was made 30 years into the life. And there are still some uncertainties about, like you mentioned, the unknowns that communities might have to prepare for. For example, we're seeing that repowering is not being regulated in the same way that decommissioning is currently. So things like decommissioning bonds and decommissioning plans may not address repowering activities. They may not address the economics of repowering. For example, if a turbine is made much larger, does that impact things like landowner payments or tax agreements? A lot of that stuff is not currently known on a national scale, and we know it's something that communities have uncertainty about. So it is something we are actively exploring, but I will toss that one over to Chloe if she has anything to add as well.
Yeah, I might just tack on to that great answer, Matilda, and say I think this is also an area where we can learn a lot from Europe and how they're approaching some of this, because they're doing a lot more, both repowering and decommissioning. So we've seen over there, for instance, building flexibility into the agreements like you mentioned. So for instance, instead of specifying what you're going to do for decommissioning, leaving it a little bit open and flexibility and saying according to best practices at the time, assuming that there might be significantly different best practices in 20 years time than there are now, and making sure that the agreement accounts for that and allows for that to happen. I think we've also seen agreements that specify certain points in the project's lifetime where there's a requirement to come back to the table to discuss where the project's at and what the sort of decisions are that are on the table at specific points in the project lifetime, which I think is really helpful in keeping communities involved and aware of that decision making.
Awesome. Let's see. I'll toss this one to Derek.
Yep.
Do you see the need for federal financial incentives such as ITC or for the industry to implement recycling, and how else wind turbine recycling can be catalyzed and implemented in the future? So related to tax.
Yeah, it's a great question, and I don't know that the ITC or PTC has a direct relation to the amount of blades that are recycled at the end of their life. I do know that we are looking at regulations, and so we are within the IEA are looking at recommended best practices, which may eventually become into the IEC, which is the International Wind Turbine Standardization, how we design and build and deploy, and we don't have a whole lot of standards at the end of life, and so we're looking at having standards down the road that can basically govern how end of life and recycling of wind turbine blades happens, and how much has to be recycled, what types of recycling, what types of LCA has to be done in order to understand the emissions and things like that. So I don't know that it's necessarily tied right now to federal incentives, but to commercialization and sort of the technology research that we have to do to bring the cost down, the organization that we have to do with the U.S. and global wind energy, as well as research institutions to develop the pathways to recycling, and then the commercialization of that, and so that we have proper channels to be able to recycle. So I don't know so much that right now it's tied to incentives from tax credits and things like that. It could be. I don't know of that though.
Awesome, thanks. I'm seeing a question with a lot of upvotes about offshore wind, and this might be something we all have some insights to share since it's sort of broad. Can you touch on any challenges unique to the decommissioning of offshore wind turbines? This is something that is kind of an active exploration by DOE and NREL, but at early stages, since offshore wind industry is, getting its feet right now. It's kind of challenging to add a new complication to things, but it's definitely something that we can learn from Europe, where they're starting to consider decommissioning some of the early projects over there. Essentially, anything that's difficult about the supply chain for building offshore wind is also going to be a challenge for decommissioning. So the fact that like vessel availability and having the vessels that would be needed for that, port availability, having space to store components, the processing and all of that will be different, because along the coast tend to be more populated areas with less land available for building new things like recycling facilities or expanding landfills. So everything that's difficult about installing an offshore wind turbine, like weather and environmental impacts and all those things, will also be present on the decommissioning end. This is something that's available though in the construction and operations plans that for any of the projects that have already been built or in the permitting pipeline. You can read their decommissioning plans that are required by BOEM and the Bureau for Safety and Environmental Enforcement, BSEE, in there for any of the projects that you're curious about. But I would be interested to hear what Chloe and Derek have to say as well.
Yeah, this is a big topic. We can't probably do it justice in a short answer, but maybe I'll highlight like an example. For instance, we see an artificial reef effect happening in offshore wind turbines where there is marine life that attaches itself and sort of grows around the base of the turbine when we're looking at fixed bottom offshore wind. So that's something to be considered, because it's going to cause a lot of disruption to then remove these structures that marine life has grown around. And so that's something that Europe is looking at quite closely, because they're a little bit of ahead of the curve on us. And it's just one of many examples of things to be considered for offshore.
And Matilda, I don't have anything to add to that. But if you're okay, there's a couple questions on LCA I can combine into one answer, really, if that's okay.
Yeah, sure.
All right.
Let me just
Sure.
read them.
Oh, sure.
Let's see. And actually, just one last thing on the offshore, and that I'll
Yeah,
add.
sure, please.
Recycling will be a little bit different as well, because the composites used for recycling have a somewhat different makeup. So that's something that's
Yeah.
also being explored in research as
Yeah.
well. So with the LCA, one of the questions was, for LCA, have environmental impacts beyond emissions been examined for various recycling methods for composite materials? And then there was another one about LCA, whether it includes manufacturing. So those are the two that I see. If you saw any others, feel free to answer them.
Yeah, so I'll start with the first one that you read, which is other metrics, and absolutely, and I'm not the LCA expert. We have a team here at NREL that does that. Greenhouse gas emissions is just one of the, and it kind of is one of the most visible sort of, as people look at what metrics are out there. But there's, we put together a table of about 30 metrics, and then we prioritized about 10 of those metrics. And those are in the report that Matilda had talked about, looking at human toxicity, looking at cost effectiveness, looking at many different things within the output of the LCA that measures what type of impact that every single recycling method will have on when we recycle blades. So we did do that. I don't have the answers at the top of my head right now, but it's in the report that we did. As far as the LCA going outside of recycling, we actually did, we expanded the boundaries to include the decommissioning process all the way through the reuse process. So expanded those boundaries a little bit. So we started a little bit earlier on the decommissioning side, and then the remanufacturing side as well. We didn't right now in this project extend that to be back to the manufacturing of the blade. However, many of our colleagues here at NREL and in other national laboratories as well, and in the industry have done that. So we have other LCA projects that look at the raw materials coming in the door to manufacturing and the manufacturing itself, and what that looks like for metrics of LCA. So it does exist, just not part of the report. The report that we put together was focused very specifically on decommissioning through remanufacturing, that recycling process as far as the report goes. Yep.
Awesome. Thanks, Derek.
Yep.
Another one we have is, depending on the decommissioning process, and I don't know if any of us will know the answer to this, but I think it's an interesting one, controlled demolition versus disassembly. Is there a better opportunity for recycling the components depending on the decommissioning process used? Looks like Derek maybe has an answer.
Yeah, I'll jump in. From the blades point of view, we would much rather a measured takedown of blades and things like that. I've seen, not personally, but I've talked to the companies and seen pictures of the ones that are demolished and the blades splinter, and it's really kind of a mess on the ground, and you lose the possibility of using sections of blades that have long fibers, and therefore the strongest and stiffest part of the blade itself, and you can whether it's reuse or even some sort of mechanical or thermal or chemical recycling, you're actually losing the ability to use long fiber with that demolition sometimes. So there's no question that of all of the different processes of bringing a turbine down for the composite materials, it very much would favor a crane decommission of the turbine itself. I'm not sure, Chloe, if you have any other any aspect to that. Yeah, okay, gotcha. Yeah, yep.
That's a good example of something that might not have necessarily been included in a decommissioning plan or decommissioning requirements. Right. It kind of shows how the two parts of this, or the multiple parts of this, should be talking to each other more.
Right.
If you knew that recycling in a certain way was going to be desired towards that of its life. And maybe just one last question. Let's see if there's any more that are kind of on the stakeholder side. Okay, so there's a question about the availability of information about what recycling facilities and landfills are out there, and that is something that came up a lot in our stakeholder and community engagement work, that folks would like to know that information mapped out to help kind of understand what will be happening to the projects in their area or under their jurisdiction. That's not something that currently exists, but it is something that we have proposed working on in the future. Mapping these things out would be something that would help the industry and decision makers kind of understand where things are currently. And so I'll just say that that is something we would like to see as well, and hopefully we'll see in the future. And with that, we have just been about a minute left, so I'll wrap up by saying thank you so much for joining us and spending part of your Thursday morning or afternoon, depending on where you are, learning about end of service and recycling for wind energy. Thanks to our speakers, Chloe Constant and Derek Berry, for sharing their expert insights with us. And thanks again to the DOE Wind Energy Technologies Office for supporting this webinar series. We look forward to seeing you at future webinars, including our final webinar of 2024, which will take place in August. So have a great day, and you'll get the recording and everything else in your inbox in a couple of weeks.
Thank you.